Flavio is a postdoc in the section of physics at the Faculty of Sciences in Geneva. He did his PhD at the University of Vienna, and he works on quantum foundations, and I guess in some sense also in the philosophy of quantum physics. Today he will be speaking about potential realism, classical and quantum indeterminism. Please, Flavio.
Thank you very much, Chris, for an introduction. Thank you all for having me here today. So the work I'm going to talk about today is, well, at the same time, a new view that we have developed, and also somehow I will spell out a whole research program that I've been exploring with Nicolas in the last few years. So let me get started. The overarching program is to explore the possibility of having fundamental indeterminacy and how this leads to indeterminism in physics. Of course, I mean, as Chris kindly said in the introduction, I've been working mostly, so my background is physics. I've been working mostly in quantum foundations and quantum information. So clearly there is something that indeterminism is very much discussed, and historically that's where quantum mechanics was the theory that brought about the broader discussion of the fundamental level of indeterminism. But what we've tried to explore is also to take a step back and go to see if in more general or in theoretical frameworks that are considered to be fully understood as deterministic, one can have some room for discussing indeterminism also there. So let me start with classical physics. What I call the orthodox interpretation of classical physics, the one you find in textbooks, the one you always study as an undergrad in physics for sure, tells you that, well, the structure of the theory itself is deterministic. Why so? Because you associate to the state of a system, for instance, let's say a point particle, you associate to this a state as a mathematical point in phase space. Okay, so the maximal informational piece you have about a classical physics system is this n-tuple of real numbers that characterize its states in phase space, so in momentum and position. And then you have a certain set of dynamical laws that in particular in classical physics, in Newtonian mechanics, that say they are ordinary differential equations that have a unique, given the correct amount of initial conditions, which is provided by the initial state, you evolve uniquely the state in phase space. This characterizes a unique trajectory both in the past and in the future. And there is mathematical theorems about ordinary differential equations that tell you that this continuation ad libitum in the past and in the future is unique. This is how determinism comes about in classical physics. So try to pin down what are the assumptions that I have spelled out here. So you need infinitely precise mathematical point that characterizes the state of a system in phase space plus dynamical equation. The combination of these two give you the unique trajectory in past and future. That's what leads to classical determinism. I want to point out a very small, but I think interesting historical fact, that the first doubt about indeterminism don't come actually from quantum theory, but already at the time of statistical mechanics, some scholars, this is called sometimes in the literature of historical literature, Vienna indeterminism, because Boltzmann already started having doubts about the fundamental deterministic nature of particles. And he thought maybe the fundamental equations for individual molecules will turn out to be only approximate formulas, and you can only get average values. So he started to believe more radically in a statistical interpretation. And a contemporary of his, less well-known, Franz Serafin Exner, pushed this much more, saying that everything that happens in nature is the result of random events. So he really introduced this idea of randomness before and independently of quantum mechanics. And even Schrödinger, who is considered, well, the person after whom is called the Schrödinger equation, which is the deterministic evolution of classical physics, and is considered more on that side of the on the non-collapse side. He was a direct student of Exner, and he said that probably not microscopic lawfulness, but perhaps absolute accident formed the foundation of our statistics. So already at this time there was some ideas. Okay, following the more mainstream historical development is indeed, as I said, quantum mechanics that brings about the more radical doubts about determinism. The two main results, I would say, that characterize quantum physics that give us the hint that the world might be indeterministic, that quantum mechanics cannot be reduced to deterministic theory, is Heisenberg's uncertainty relations, which, unlike what I showed you in the previous slide with the state of a system in phase space was a mathematically infinitely precise point, Heisenberg relations put a quantitative bound of the minimal size of what can characterize a state in the volume of a state in phase space, characterized by the Planck constant. Of course, Heisenberg can be overcome if one explores all the logical possibilities, because you can think that there is some incompleteness in the theory. So it's a problem of the theory and it's not characterizing something really out there. And you can actually introduce additional variables that were not encompassed by the theory, by the quantum theory itself, and try to recover indeterminism. So this is something that is in principle possible. But then Bell's theorem came about, and Bell's theorem is even more radical in our rethinking of indeterminism. So under certain easy assumptions, I will also spell it out a bit more later, but if you believe that you have a separation of systems, so some form of locality encompassed by independence of measurement settings at different locations, if you have a minimal amount of this independence, then there cannot be a model, a deterministic causal model that explains the outcomes of an experiment. So somehow Bell's theorem, of course, under its assumptions that you can still question, so that there is always room to push. But let's say quantum mechanics has more and more hinted at this possibility that the world might be actually indeterministic. So Bell's theorem is something that can help us. I will tell you later, but can help us really provide new, genuinely non-predetermined outcomes. Okay, so as I said, this idea of indeterminism in quantum mechanics has led to a fierce debate in the literature of trying to understand, so based on different things. One is the solution to the measurement problem, but one of the features that separates different interpretations of quantum mechanics is whether they are deterministic or indeterministic, whether they try to complete the theory and get back to a deterministic theory, or if they take seriously at the fundamental level the indeterministic character of the theory. So this kind of table, the right-hand side, is kind of clear, well understood, and the foundations of quantum mechanics. Nobody would object that you can interpret the theory in different ways, some of which, for instance, Bohmian mechanics takes the initial position of particles to be the hidden variable that is missing in the theory. And if you complement the theory with these additional variables, you retrieve unique trajectories in the same sense of classical physics. So you have a deterministic interpretation of quantum mechanics, although these things are not knowable. Okay, there might be fundamental problems, but let's say you have a way theoretically to retrieve the deterministic trajectories, whereas the standard, let's say the orthodox interpretation of some kind of quantum mechanics, if you take seriously some kind of collapse, either subjectively or objectively, you need to introduce some to take the probabilistic behavior of quantum mechanics as a fundamental feature of the theory. So you have a series deterministic theory. What we have explored is this left-hand side. So trying to understand whether it was somehow a historical contingency that led to people to all agree on the deterministic character of classical mechanics, whereas there is at least a logical possibility, and should we follow that? So under what assumptions and how far can we develop this? So the idea, let's say, somehow of the whole program is kind of to symmetrize this figure here. What lies there in the upper left corner? Okay, there is more to this. Not only there is the logical possibility, but perhaps there is reasons to try to explore this idea, because what I presented as the orthodox interpretation of classical physics, to have this mathematical n-tuple of real numbers that characterize a mathematical point in phase space, relies on an unstated assumption, which we call the principle of infinite precision. So when you take the textbook of classical mechanics, and in the first page says physical quantities take value in the real numbers, they are assuming that you have this infinite precision, not up to an arbitrary amount, but really all the real numbers do represent in the theory valid points of valid states, valid physical states, all given at once with infinite precision. Because if you would have any amount of imprecision in this number, if you would have a tail that is not fully determined, this then would not satisfy the theorems that lead to the single extension of a unique trajectory in phase space. Okay. So somehow there is this unstated tacit assumption in standard quantum mechanics that there exists at any instant in time classical mechanics, there exists an instant in time at every instant in time an actual value of every physical quantity with its infinite predetermined digits. Anyways, with the infinite amount of information that the real number contains. What Nicolas has started, and I joined this program, we have wrote quite extensively about this. This was our first main paper where we spelled this out, is that you can relax this principle of infinite precision, assuming, for instance, a principle of finiteness of information density, that in a finite volume of space, maybe space-time, there can only be a finite amount of information. Therefore, having this infinitely long string, this infinite real number, unstructured real number that contains an infinite amount of information in general, should be forbidden. And we should try different alternative interpretations. And we followed this idea to see where we can push it. And I will talk more about a specific model based on this later on. So in this view, just to remain at the general level, initial conditions are not real numbers. They're not infinitely precisely determined. And on top of this, so you have some, if you think again of the picture of the phase space, you don't have any more mathematical point, but you have a certain finite volume, not specified in size or in shape for now. But it's enough to have an epsilon, infinitesimal difference from a infinitely precise real number. This plus the existence of chaotic systems, which, by the way, are kind of it's a bit of it's a shame of the physics. They try to hide until you are quite grown up as a physicist. We are always live under the spell that everything is harmonic oscillators, everything is integrable. But actually, when you start growing up as a physicist, you realize that almost all, in a mathematical sense, of physical systems are chaotic. It means that you can basically enlarge as much as you want the initial indeterminacy that you put into your equations of motions, and the indeterminacy can grow exponentially in time. So basically, having any single infinitesimal of initial indeterminacy in the state leads to multiple trajectories that can be really saturating the whole phase space if it's chaotic. So you can enlarge your indeterminacy as much as you want, keeping the same set of dynamical equations. So we are not here claiming that there is some fundamental stochasticity in the dynamics, but really just assuming that there is a bound to the precision, so that the precision is finite, leads to multiple trajectories, therefore to a non-determinate, so an indeterministic evolution. And in this way, it is very nice what Nicolas has thought about this, that you can think of the real numbers as the same way that you think the initial positions in Bohmian mechanics. You can think as the real number as the hidden variables with which you complement this fundamentally deterministic theory, and you can make it deterministic by adding by hand all the holes, putting the infinitely precise real numbers in. So you have this. If you put the hidden variable real numbers, you get the standard orthodox interpretation of classical physics. If you instead put this finite precision, principle of finite precision that we adopt, you have an indeterministic theory, an alternative indeterministic interpretation of classical physics. I call it interpretation in the same sense for the jargon that is used in foundations of quantum mechanics, where you call interpretations everything that keeps the same mathematical structure, let's say, of the theory, the same set of equations. And so, for instance, the objective collapse, GRW, and so on, they're called usually theories because they have actually different predictions and they modify the linear evolution, whereas the Bohmian mechanics and the standard quantum mechanics are called different interpretations. And in the same way, you can think of these two as two different interpretations of classical physics. And so again, just the pictorial is what I just said. If you have the infinite precision, you have this leads to unique trajectories and determinism. If you have some finite precision, you end up in multiple possible trajectories in the future, and also retrodictively in the past, if you want. So we'll talk a bit about this. And this clearly evens out a bit the difference between classical mechanics and quantum mechanics, that are supposed to be one of the main feature of, well, the main characteristics of quantum mechanics that was considered revolutionary with the old paradigm of classical mechanics, is that it forces us to be indeterministic. But actually, if you take this approach, you see that the only difference between these two is that you don't have an H bar in classical physics. You don't have a constant of nature that is quantifying how small is the smallest amount of volume. We only impose that this is finite. But it leads to similar conclusions on for what concerns indeterminism. Yeah, so indeterminism in the initial conditions leads to indeterminism in the trajectories. Two quick remarks about indeterminism, just to maybe prevent some criticisms that I've heard several times. So often people are telling me, yeah, but you know, there is a two-body system, there is harmonic oscillators, there is regularities that we observe continuously in the world. What do you think that the world is indeterministic at the classical level? Again, I don't take indeterminism to be any lawless form of either epistemic or ontological level. It's not something that means that everything is completely random, that there is no regularity, that there are no laws. We take it at least as a sufficient condition, that there is some, perhaps just a few. I mean, if you believe me on this thing of the chaotic system is most of them, but even if there is one event, or perhaps a class of events that are not deterministic, this is enough to call the word indeterministic. So indeterminism is a sufficient condition. You don't have to have, it can coexist with regularities and even some deterministic conditions. Most of my talk will be also about this. And the second remark is that even taking it as a sufficient condition is somehow, if you trust the meaning of the assumptions of Bell's inequalities, you can use them as machines to amplify the indeterminism in the same way I told you at the beginning. So you can actually, if you have reasons to believe that you can have independence between the measurement settings at distant locations, you can, and if you have at least one event that is not predetermined in nature, you can use that as an input to get this independence. And then the device-independent violation of Bell's inequalities ensure you that the outcomes were not predetermined. And since you can have like more outcomes than inputs, you can generate basically more and more bits and use those as a chain reaction to generate more non-deterministic. So somehow, if there is one event plus the violation of Bell's inequalities, indeterminism can be inflated. Good. So this was more or less the general idea that we have already. We have written already quite a lot about this, but today we'll focus more on a new work that originated from. So it's more the philosophical background of all of this, and somehow it's a new view on how you can regard physics in different theoretical frameworks. So this thing is not attached to either classical or quantum mechanics. It could even be about some fictional theories or some post-quantum theory that we will have one day, perhaps. So one feature of an indeterministic physics is that the world should be able to produce events not by necessity. So you can have new information that is produced. And so you have a concept of something that is not predetermined after a certain time. And then you have the concept of this creative time is in this very sophisticated animation. You see that you have a poof and something that was not determined before, a bit, for instance, gets determined. So you have the concept of change, at least. Okay, so you have the state of determinacy of this preposition J is equal either to 1 or 0 is not determined at the beginning, and it gets determined after a certain moment where things actualize. So you have the concept of, so what is this thing at this point? This is what we have to investigate. So we know that here you can measure it and you have a single outcome, and you go there and you check and it's a 0. But what is this thing before the poof? So you can think that the new information that gets here created, it has no structure. It's fully random, and you have events that are not acausal, as has been thought many times in the literature devoted to indeterminism, including from some philosophers and logicians. For instance, Lukasiewicz was like thinking that you need a multi-valued logic where you have like some chains of events that at some point they just get generated out of the blue, out of nothing. You have a random event that creates information with no causal connection from anything else in its past. However, this is not the view that we endorse here, but we endorse the idea that a second possibility that one can explore is that events like this can exist and do exist indeterminate up to a certain point when they get actualized. And before, what exists is a well-determined potentiality. So that there exists at the fundamental level, it exists by saying it exists, I give objective reality to this, to what I'm claiming, that there exist out there in the world potentialities. And my talk will be mostly about this now. So let's go back to the idea of a physical state. What defines the objects that are around us? What defines the things that we claim our theories are describing? So a physical state, if you take let's say a realistic interpretation of theories, but let's say in any physicist probably more or less would say this. So according to Butterfield, is a physical state is a system's maximal or complete set of intrinsic or possessed properties. So we tend to think of our objects as collections of properties. So you identify really things through their collection of possessed properties. So In the standard physics, you have that outcomes are manifestations, so outcomes of measurements, if you go there, are manifestations of pre-existing, fully determined possessed properties that you unveil by asking nature, how tall is this bottle? You go there, you think that the length of the bottle is an intrinsic property that this bottle possesses, and then you go there to unveil it up to a certain precision, but you believe that you can always get better, or even if you don't have to get better, you postulate that this thing is well defined with its collection of properties. I already stressed enough that this collection of properties are usually assumed to be real numbers, therefore they are like infinite complexity, infinite information into them. And they are assumed to exist at any instant in time. Our alternative view that I'm presenting here today, we call this potential realism. So it's a form of still looking at nature with a realistic viewpoint. So you keep up, you can still uphold a realistic view, things do exist. Causality still relates events, and I will discuss this in a moment. But potential realism means that the outcomes of measurements are dynamically realized. They come into existence creating new information from a collection of different possibilities. There are mutually exclusive possibilities, and then what you measure as times unfold, or when you have to inquire in nature about something, it returns a single outcome that is dynamically realized out of all its possible potentialities. So before the realization of one and only one of the outcomes, the element of reality, the state itself of the system, it's the collection, maximally informationally complete, maximal amount of information about the system is the collection of its potentialities. Associated with, in physics, associated with each possible and in general still indeterminate outcome, if you think in terms of experiments. Okay, what are these potentialities though? So potentialities are some kind of, you have to think of this as some kind of intrinsic tendencies, dispositions of systems. And we want them, so this kind of list of desiderata, we want them to carry out the causal structure because we clearly observe in the words of this kind. I would take causality as an observational fact that I can poke the word and it will react. So there is causation in the word, and we maintain this as a fundamental feature. We want to have some compatibility with the objectivity of the external world. So we uphold some form of realism, but we don't want this to be governed by necessity. So causality and realism at the same time without necessity. So causality, realism, and indeterminism would be the tenets of this view that we are developing here. The tool that we use, the way we call this for historical reasons, clearly, and we have drawn a lot from discussions in the literature. These are propensities. These are called there have been called propensities, at least since Karl Popper introduced in the 50s. Karl Popper thought of them as interpretations of probability theory, actually. So for him, it was among the different subjective and objective interpretations of quantum theory, of probability theory, classical probability theory and quantum probability theory. So he was stimulated by the idea of quantum mechanics that required to rethink the interpretation of probabilities. Anyways, here, don't think of them as probabilities. Think, for the time being, I will discuss the connection with probability, but for the time being, don't think of these propensities as probabilities, but think of them as causal relations that relate events or the intrinsic potentialities of physical properties of systems to realize one of the possible outcomes. So they are time dependent, clearly, because they can evolve. And we adopted the same writing as in probability theory for conditionals, but this is is to be interpreted as a P of the event A given its causal conditions is the tendency of the event A to happen. For instance, the outcome of a measurement to show up the result A, given the relevant causal conditions that can influence the realization of that outcome. So it has a certain amount of things that can causally interact with this event that if counterfactually they would have been different, would influence the outcome A to show up. And for instance, this can be the setting of an idealized measurements. I will discuss this later. And we deem propensities to be necessary in the description of a causal and indeterministic theory in the same way that actual properties are necessary to describe an indeterministic world. Okay, propensities have been, as I said, they had quite a lot of discussion in the philosophical literature devoted to interpretation of probabilities, and we propose our own view of propensity here that we claim is more suitable for describing this kind of tenets that I have presented of causality and realism in physics. So we want our propensities to be single case. What does it mean, single case? It means that they characterize the objective tendency of an individual event or the individual properties of a system to realize. So they're not something that belong to a long sequence of trials, as other authors like Gillis and others have proposed. Having propensities, thinking of propensities as belonging to, as a somehow the objective manifestation of a whole long run sequence of trials, possibly infinite, would entail some kind of a non-locality in time, because this trial can take infinitely long. And if you ascribe an element of reality to this thing, it means that there is something already there objectively existing that has information about everything about the infinitely in the future in principle. So it's something that again encompasses an non-locality in time, possibly infinitely in time. And we want them to really characterize the appearance of single outcomes in a single trial. So it's something that belongs really intrinsically. Yeah, the second property is that they are intrinsic property of a system. They are quantified tendencies to realize a particular idealized measurement outcome when subjected to the specific circumstances, therefore to the complete set of causally relevant conditions. So it's an intrinsic property of the system, somehow caused by its all the possible connections that can influence causally the outcomes of the specific outcome. They are indeterministically causal. They quantify the degree of objectivity of the possibility. So the future is open, there is different possibilities, and they somehow characterize the strength of how a possibility can realize, can obtain. So you can think of them somehow, so if you want to imagine them in the word like a Newton was thinking about forces, that they actually exist connecting things, that you can push things. They're part of the ontology, if you want, of Newtonian mechanics is that there is these forces. You can think here as having these potential forces or indeterministic laws that are actually connecting causally different things that can interact, but non-deterministic. And we postulate them to be an element of reality, as I told you, the causally connected events. So, propensity allowed to think of events as actually developing in time. One way you can think of how to represent these propensities, for instance, in a causal graph, so is a DAG, is a cyclic graph, because you want to have a direction of causation, and in particular in this case is a multigraph, the way I represent it, where the blue arrows are actually the possibilities. So this blue graph is the structure of everything that can happen, And the red arrow is what actually happens. So when a propensity becomes of maximal strength, it becomes certainty, it will turn the color of the arrow into red, basically. Okay, so you have the red graph is the actual story of what has happened, and then you have certain things that might have happened and they evolve in time and they are ruled out now, but they were possibilities. And then in the future you have non-trivial propensities where, for instance, this thing here can happen with a propensity of 1/4 and this of 3/4, for instance. So you can have bias different weights for events to happen in the future. So intrinsically, this idea that there is an becoming, there is an evolution, an intrinsic time of realization of these propensities, also indirectly defines the concept of present as being somehow the manifold, perhaps with a certain thickness. It doesn't have to be like an instantaneous present. It can have a certain thickness. We discussed this in another paper. But the concept of present is somehow the surface, the hypersurface, the manifold that separates the subgraph where all the propensities have been already actualized. They have already a determined value of 0, 1 from the one that you still have an open future. So you still have non-trivial propensities of 0. Okay, a small remark I want to make is why would you adopt such a metaphysical view on these real existing propensities? So a general remark is that we believe that metaphysics, in particular ontology, is a very important tool for it's a very important part of our scientific theories, to the extent that they allow ontology allows you to tell stories, to give the explanatory power to a theory. You are allowed, you postulate existence of certain things that are in accordance with so that they're not in disagreement with observational facts, that they are empirically adequate, but you postulate the existence of certain, it allows you to name things and to tell a coherent story on how things move and interact and change shape. So you have to introduce this kind of terminology and believe that this thing exists in the world for the strength of an explanation. And each theory and interpretation comes indeed with a specific ontological position. If anything, the negation thereof that is meaningless, this is meaningful. But in general, you have like the concept of particles, rigid bodies, etc., etc. And each ontology, in my opinion, has somehow a cost. So once you adopt an ontology, you have to see how costly it is. Okay, the cost is the currency is arbitrary, but let's say. You can somehow identify what are the features of an ontology. For instance, I think starting from an example is Anaxagoras' seeds. In ancient Greece philosophy, Anaxagoras was saying that everything was made of seeds that were like kind of miniaturized versions of all the things. Everything had miniaturized versions, and the composition of, so in everybody there was a bit of everything else. And the percentage and the composition of this thing was giving you why you look the way you look. Why a chair is a chair, because it's made of very tiny piece of very tiny trees, plus very tiny homunculus. It was made of everything else and this composition. So this is clearly an ontology that is very costly in terms of the amount of fundamental entities that you have to introduce in the world to explain everything else. Same somehow in the much more modern interpretation of quantum physics, the many words interpretation, to explain why you see an interference in the Mach-Zehnder interferometers on a 1 meter tabletop experiment. You have to pay this huge price of believing that the world is continuously splitting in infinitely many, coherently splitting in infinitely many copies of itself. So I maintain, at least at an intuitive level, that these ontologies are very costly. You have to, it has a hyperinflation of required things of the word to explain our scientific facts. Why I like the potential realism that I'm here presenting is because I find it very cheap, very inexpensive at the ontological level. Because what we observe, and we always, ever, since the beginning of observation, since the beginning of science, we have only exclusively observed statistics. So what science does, even in classical physics, you observe statistics. You only can just statistically say the range where things are. So somehow probabilities or some kind of measure of likelihood is really intrinsic to the way we have ever produced science. It became somehow in our mind more fundamental with quantum physics. It seems to be indisposable with quantum physics, but this was always there somehow. So having a theory that starts from somehow from a measure of likelihood as the element of reality sticks very closely from what we ever observed in our scientific theories. And it's not epistemologically more mysterious than the standard view of classical physics, where you have an possessed property, because the only way to supposedly unveil this existing property is to measure many times and collect the statistics long enough. And our propensities will be measured by sticking to some law of large number, in the same way that you collect long frequencies and you approximate probabilities. So somehow the way you get to know propensities and the way you get to know the alleged actual value of things is epistemologically the same process. You just have to repeat trials and approximate what you think it exists out there. Okay, now that I made a big propaganda of propensities, I also tell you some problems of propensities that have that needs some consideration. So one problem of propensities, as I told you, propensities developed as an interpretation of probability theory. They were supposed to be objective probabilities. And this was the way that Popper designed and popularized them. However, in the early 80s, Humphreys put out a paradox that can be formulated in a kind of a no-go theorem. So more than a paradox, it's really it's a theorem, let's say, that tells you that if you take these two assumptions, not very visible, propensities quantify intrinsic causal connections, single case intrinsic connections in the way I told you, plus propensities are probabilities in the sense that they satisfy Kolmogorov axioms and from which you can derive a Bayes rule. These two together cannot be upheld, so they lead to a contradiction. And the most basic way of seeing this, there is more sophisticated and versions to prove this, but let's say at least an intuitive proof of this theorem is the following. Bayes rule is this rule of probability theory that tells you that if you have a conditional probability distribution, you can write, so of an event given its cause, you can write it as a function of the reversed one, of the probability of the cause given the event, except in this way, with the absolute probability of P of the event given P of the cause. At the same time, however, you want the cause and the event and the effect to have meaning. We call cause and effect because they are asymmetrical. You want the effect to be influenced by the cause, but not the cause to be influenced by the effect. Therefore, the probability of the cause given the effect should be just independent of the effect of the cause given the effect should be independent of the effect itself. Okay, you plug this thing into here, and you find the probability of the effect given the cause is also independent of the cause. So if you want the propensities to satisfy premise one, that they actually encompass some causality into them, they either are causal in both directions from the past from the cause to the effects, or neither of them. That's somehow the way you can see unphrased paradox. So as every no-go theorem, you can drop, well, the conjunction of the assumptions is wrong. It's false. So you can drop both or one of them. You can decide which one you want to drop. Dropping the first assumption typically leads to what I was telling you at the beginning, that you need to have propensities not associated to single events, but to whole infinite class of events. Therefore, you have this unpalatable non-locality in time that we have already excluded. Therefore, we prefer to drop the second assumption and say that propensities actually are not probabilities. They cannot fulfill all the axiom of probability calculus. However, there is a but. Of course, they cannot also be arbitrarily distant from probabilities. Why so? Because for sure we want them, since we want them to represent, so we want them to be somehow measurable and to be compatible with our observations, we want propensities to have some form of, we want to epistemically relate them to observation, this element of reality to observation. So we want to have a law of large number. This Bernoulli's law of the weak law of large number that tells that the probability, okay, this is usually derived in probability theory, that tells that the probability that a certain observed frequency of n trials is distant from the actual probability. So it's a probability that the probability is different from the frequencies tends to 0 for n that goes to infinity. We want to keep these kind of things, but this big P will still be a probability, but this mod B will be a propensity, which also removes a bit of the circularity in the definition of probability, where you have in the operational justification of probability. So this big P is a probability because somehow it tells you what is the correlation, the observed correlation between the actual propensity and the finite amount of trial, the sequence of trials that you have done. This tends to 0. So that's the element of reality. That's what you can observe, and this tells you what is the correlation between the two. So probabilities still are a good. We're not claiming here that we should abandon probabilities. Probabilities should still be used in the same way they are. However, they represent another layer. Probabilities exclusively encompass correlations and not causations. If you want to use this kind of likelihood, measure of likelihood for a causally connected element of reality, you need to abandon propensities. But both of them, probabilities and propensities, they should satisfy this law of large number, so they have this in common. Both of them want to encompass certainty and impossibility. So probabilities, well, somehow probabilities are not supposed to be an element of probabilities are not supposed to have an objective, they're not physical principles. So it's not really impossibilities and certainty, but you want somehow to have them bounded between like something that can happen and cannot happen. And the same is with propensities, obviously, even more, because here in this case is really what causally can happen. They're a principle of physics. And finally, if you want propensities to be adequate for describing quantum physics as well, they must show some kind of non-locality. So they have to be non-local in space with it. Some events should be correlated non-deterministically, but happen at the same time in different locations. And for this reason, the propensities are not probabilities, but similar to probabilities. In the literature, these have been called non-Kolmogorovian probabilities, in analogy with non-Euclidean geometry that keeps most of the structure of the geometry. You can derive most of the theorems, but then you can still have a consistent theory of geometry without the fifth Euclid's axiom. And here you can drop the axioms that lead to the base rule, but keep some. How much time do I still have? 0. Okay.
We should leave some time for discussion.
I'll slowly draw through the conclusions. Okay. Okay, this I just go very quickly. I just wanted to tell you that this is we have used propensities in deriving our in designing our alternative non-deterministic interpretation of classical physics, which we call based on physical finite information quantities. And so we have actually done a model of this based on propensities, where each digit of a physical variable is associated to a certain propensities, which is a finite containing finite information being a rational number between 0 and 1. And this quantifies the disposition if you take, again, the length of this table in a binary expansion. Each digit of the length of this table has a certain propensity to realize to be 0 and 1. And then a finite information quantity is the element of reality somehow, is the collection of all the propensities of all the possible digits, and such that it has a total finite amount of information. So for instance, one way to achieve this is that after a certain point, all the propensities are 1/2, like are totally random, and this is compressible string, and it has finite information. Okay, so this is just to say that we have somehow filled this corner that I wanted to fill at the beginning. I'll skip this. I just wanted to tell you that we have discussed this in the context of special relativity. Still some work has to be done, but let's say special relativity forces us to adopt relativity of indeterminacy. So for different observers, something that is determinate exclusively within the light cone and not for stuff that are outside the light cone. We have a paper on this, and that this can also lead, not this particularly, but that in the fundamental indeterminacy together with the finite information quantities can lead to the possibility of an open past. That's, yeah, I just wanted to show some literature that we have produced on this. Yeah, Nicolas has explored also the possibility that this might be a problem of mathematical language. So the fact that physics hasn't evolved into this more indeterministic direction is because our mathematics is very platonistic, monolithically given infinite information, pieces of infinite information all at once in the form of real numbers and functions with real numbers. But Nicolas has explored the possibility of using intuitionistic mathematics, where the concept of evolution of time is directly embedded into a different mathematics. So you might think that there is a strong connection between physics and mathematics in this discussion. And finally, I want to discuss that another feature or problem that arises in indeterministic theories is a kind of a classical measurement problem. So every time you have some potentiality that has to realize to become actual, you have to specify what is the mechanism, how, when, under what circumstances this actuality becomes from potentiality. So the transition from potential to actual. And you want measurements to keep a certain amount of tainets. You want stability. You want that if you measure twice the same system and you have already found the digit, this is not changing in time. And you want precision in probability. If you go there, if you couple an instrument of measurement to this table, which is more precise than the measurement I did yesterday, you want a new digit to uncover. So somehow you want nature to react to how good you are at measuring it. And this leads to the same problem of quantum mechanics, of why from a superposition you see only like you have a Mach-Zehnder interferometer, why you measure only, if you put in the middle a photodetector, why you see only the spin that is up, for instance, instead of the superposition. So how you have the Copenhagen interpretation that has some sort of it requires a Heisenberg cut of something that lies outside of quantum theory, some classical counterpart to the theory that is responsible for the collapse to happen. And in this sense, you can also have it in our classical indeterministic, in our propensity idea. Propensities get determined when a higher level, so some kind of top-down causation. You can have a higher level of description, it's a bit vague, but higher level of description is forcing the propensity to react and to get actualized. You can have the same of objective collapse theories like GRW. You can have propensities get spontaneously determined, and maybe when you measure them for some mechanism, the rate increases in the same way that GRW does with the number of particles. You can have, again, the orthodox interpretation of classical physics. You can think it as Bohmian mechanics, where you complete the theory. And finally, you can even think of a very exotic interpretation of many words, where propensities don't evolve, don't actually ever actualize, and you only have in the graph I showed you, you only have the blue part. There is not a single story, but all the stories coexist, and you subjectively happen to be in a branch. So also the many words don't seem to be unique to quantum mechanics, but to any fundamentally causally indeterministic theory. So I take a bit the conclusion I draw from this investigation I've done is a bit that many of the mysteries that we attribute to quantum mechanics are actually could have been already present, and logically are present also in a different, looking at from different direction, also at classical physics. First and foremost, indeterminism is not uniquely quantum. You can clearly think of it also in a classical theory. This leads to a measurement problem that therefore is not unique to quantum theory. And a plurality of interpretation to interpret the previous 2 points is also not uniquely quantum, and you actually can draw a comparison, quite a parallel. What seems to be really quantum is H-bar, basically, is the incompatible measurements, the possibility of doing exactly incompatible measurements, what constrains the phase space of the physical state, and also the violation of Bell's inequalities is attainable exclusively through incompatible measurements. If you don't have incompatible measurements, you cannot do this. So what seems to be really unretrievable from a classical point of view is where H-bar appears, or H. I think I'm done. Thank you.
Thank you. Let me get to here and just take the microphone from you and clear that part. And the way we're going to do Q&A is I'm going to hand around the microphone so that people will actually be recorded and audible to our audience on Zoom. So, questions, comments, objections? It doesn't need to be too close. It's okay. It's somewhere near there.
Thank you. That was very interesting. I guess I have one question about I want to push back a bit against the claims that kind of potential realism is more economical than other views. Perhaps to do that, I want to translate a few things, because we have some concepts in philosophy that probably are quite closely related to what you're proposing, perhaps not, you can let me know. So for instance, when you say that the properties are single case, or you will talk about token properties or particular properties, and that we will not say that those properties are not actual, probably say more that they are dispositional, but still parts of reality. So we have the literature on the nature of dispositional property. And it seems to me that the kind of view you are suggesting is that the world includes some dispositional properties that are tokens, are located at some place at some time, and they are not unified. It means that they can manifest themselves in the right conditions, but not necessarily. So there are different potentialities encoded in the disposition. So you can trigger different manifestations. And so in this kind of literature, you will find claims like, so you have the dispositional properties, and it's a disposition to trigger the existence of something else, another property that we call the manifestation of the property. I think how we will do the kind of ontology of those creatures. Another point is that if you want to say that your approach is minimal postulates or also approach, I think you should kind of list what does the ontological cost really of your approach, and that's try to just what are the dispositions or powers that need to. And there are different ways. For example, some people's dispositions they don't have any qualitative side, so they're not like being read, like that. It's just a purely dispositional properties. One for other persons, there are two aspects. So the property can have a qualitative aspect and also a dispositional aspect. So there are different views about what the dispositional properties are. And my point is that depending on which view you are going to take, will have there will be some cost for your ontology, but will have to include in your ontology kind of properties that perhaps you will dispense with if you were subscribing to another interpretation or theory of quantum mechanics.
Yeah, thank you. Yeah, I mean, that's okay. Yeah, thanks. Yeah, I'm aware of some literature on these positions. I think it would take very long to spell this out, and let's say I take the comments for now to look more into this. What I wanted to say is that the way we look at these dispositions, so it's not that some things have dispositions, but we take this as really as the primitive concept, like that everything is dispositional, and even things that they don't look dispositional, they have been somehow, or they are still dispositional with the maximal strength of the disposition that they are certain. So certainty and impossibility are not something that you have to add by hand here, but is just like limiting cases of this general framework of disposition. But yeah, the ontological cost, I think we have to discuss it more in detail.
So that's what
yeah.
we call dispositional validity. So everything all the way down made of dispositional properties.
I don't know this, but I would be happy if you give. Yeah, I will be happy if you give me some reference on dispositional monism. Thanks. Yeah.
So thank you for the talk. I have a lot of questions, but I'll just make maybe two. One connected with that, because in the literature on the philosophy of quantum mechanics, there was a lot of dispositionals or propensity interpretations of. You said Popper, but there was Arthur Fine or Mauritius Wilde having selective propensities, or Martin Thompson John has a beautiful, I think it's a manuscript, but it's circulating and it's very beautiful. So one question is in which respect would you differ from all these accounts, or more or less you think it's the same, because I guess that the idea is that so that the triggering conditions are just performing the measurement, and the different outcomes are weighted with the probabilities that you get from the quantum states, etc. But for me, what is more novel is what you want to do with classical mechanics and the analogies, because you said, look, we have statistics everywhere, and we look at it. We observe statistics, which is a quite, for me, surprising claim. But I mean, if in classical mechanics you say that we have statistics because we have like noise in the measurements or error theory, I think that this way of having statistics into the theory, it's very different from what we have in quantum mechanics, because in quantum mechanics we already have to implement error theory and have noise, but it seems that we have something more fundamental. And then maybe the nature of these propensities in classical mechanics is not so close to the nature of the propensities in quantum mechanics, because if I understood, I'm finishing, that idea that you just outlined, that there is the propensity that a digit within a number gets like determinate. That's but then it's a propensity of a number. So I mean, I would like to know more about the nature of these propensities in classical mechanics. How does it work? It's one digit that gets actualized, but not the other ones. If you can just expand a little bit, please. Thank you.
Yeah. Okay, start from I go in reverse order. Yeah, so this was a model that I showed you that is what you're asking me is to solve the measurement problem. So how many digits at what rate they actualize is exactly what we don't know. I mean, don't think about spin, think about continuous variable quantum mechanics. And if you have a particle that you don't know where it lies somewhere, you can think of it as acquiring position in a digit by digit. If you discretize in 0 and 1s, take the real line and you discretize it into intervals, and you take these as the digits of where the particle lies, then you can build the whole trajectory in space-time, putting where the particle is appearing here and there, right? And you can think of this both in the quantum case and in the classical case as how many digits get. So how fast and how precise is the actualization of the wave function is something that is up to debate over the different interpretations, right? So
yeah, but I mean, quantum mechanics, at least the measurement problem. The measurement. Yeah, the measurement problem is not cast in terms of having a problem of precision or having information. It's because you can just assume that one of the eigenvalues is actualized, and maybe these eigenvalues are real numbers. So I think that this is a completely different question. The question that you put for classical, maybe also for quantum mechanics. And actually, my question was, what is the analogy between the two problems? So the problem, so don't worry about infinite information. Just assume the usual story that you get an eigen state or an eigenvalue which is actualized, and it's a real number. You still have here the measurement problem, and you still have the problem of how from potentiality you get to the actuality. But then in the other case, so let's say in the classical case, in which you say that what we have is these quantities that are somehow definite until a certain number of digits, and then the propensities are associated with other digits with a number, it seems that the ontology is completely different because it's propensities of a physical system. If they are tied with digits, it depends on how you represent the number. So I would like to know more about this part, the part which it seems that is not so analogous with the usual story about the quantum measurement problem.
Yeah, okay. At no point I claim that quantum mechanics is classical mechanics, right? I mean, we are well aware. I'm just saying that this problem of actualization, if you take seriously quantum mechanics as something happening that forces you to change the description from the unit revolution to one of its eigenvalues, of course you have a completely different also mathematical description. You have a Hilbert space where you have operators, whereas here we have functions, and we have like a continuous ordinary differential equation. So clearly is not, you cannot draw a one-to-one comparison. what we're just claiming is that if you take seriously this possibility of putting potentialities into the classical state, you will end up in a indeterministic evolution, which has the problem that is common to quantum mechanics qualitatively, of deciding how and when you collapse on one single outcome over its possibilities. And this is clearly one of the main open problems of what the quantum measurement problem, at least part of the quantum measurement problem. You also have like more higher level Wigner-Spreng problems that you don't have here, but at least the problem of the transition from potential to real, I think it can be put into analogously seen in classical and quantum indeterministic versions.
Maybe also a comment.
Okay.
Yeah, let me try to react to another part of what you said, or at least what I understood from what you said. Seemingly, you believe that a classical chaotic dynamic system like the climate, let's say, is kind of necessarily deterministic, or it's intuitively deterministic and very different from any quantum system. And I think many people believe so, but only because they have been trained and selected to believe so. If you would have claimed that during your exams, you would have failed your exam. But there is absolutely no empirical fact that supports the idea that the chaotic dynamic of the classical dynamical system is deterministic. It is just a belief. But if you really seriously believe it, why not? But then you have to be consistent and move on the quantum side to modern mechanics. Make the same move as you do in the classical, where you just believe in determinism because whatever you like it, then do the same on the quantum and become a Boolean. Most physicists are not Boolean, they reject Booleans, sometimes quite strongly. And on the other side, they believe in the determinism of classical chaotic dynamic systems, and I think most of these physicists are not inconsistent. Hope I understood what you said.
Yeah. And I am a bomb.
Yeah, so I knew I was going to say that. I knew I was going to say that. That's why I'm going. I have a bunch of questions about what we chat at dinner and also suggestions. Maybe some literature, for example, on the theory of causation now, instead of which goes parallel to indeterminism. There's also some literature now on incomplete objects. It gets conclusion that's very similar to it, but it's in German. It's my own complete. So, but let me ask you something which I was very curious. And it's tangential to the main things. It's about the connection to philosophy of time. When you give us the question, because I thought that. So, do you think of it like as a new? As soon as I saw it seemed to me a new form of a theory. I'm going to say new because I think I found a beautiful metaphor for it. So I thought, okay, that's going to be new. So here's what I saw. It seems that instead of a moving spotlight, it seems that you have a moving curtain, in which once you get illuminated, right, you're still illuminated. If I draw a curtain, right, so the whole wall is there, like in the moving spotlight. But if I do a flashlight, as soon as I illuminate you, right, as soon as I pass through a ring, I don't illuminate you anymore. But then I lose the asymmetry between past and future. In both. So when I get to Chris, then I get to you. When I get to you, both him and him, even past and future. Instead, if I get the curtain, like everything once illuminated. It seems so. Are you thinking about this in that way, or am I just imagining things here? There's a moving curtain, which is out on the scene.
So you say ask Flavio as the president.
That's expenseless as someone can get. It's really a steep decline. You're the future. We don't even know the direction.
So let me just say that I've never thought about this before. So okay, let's make it up now on the spot. I think it's kind of yes, the curtain view, but it's not a curtain. It's kind of a blurred glass view because you still you see a bit of the future because you have these propensities that they might be close to certain, like since these propensities are evolving to be 0 and 1, you might have like also smooth transition. You don't have to have a immediately collapsing from 1/2 to 0 and 1. So you can have a certain thickness of the foreseeable future where you're able to give kind of good predictions on your propensities, whereas the very far future is really behind the curtain, and perhaps even the very, very, very far past, this openness of the past I didn't have time to discuss, but I believe that you might even forget the past at some point. But let's say there is a large chunk of things that you get unveiled slowly, and you have this transition zone. Yeah. There is also, I think, there is also a chat.
I'll check it. Okay. Okay, you're following this. Okay.
Yeah, well, so even before we had.
Just to say that actually there is already a view, there is it's called, I mean, or maybe it's not the very small, it's called the growing cloud of determinism of banks and chambers. So then you have a block universe, a four-dimensional world, and then you have deterministic propagating version of the future. So maybe it's quite close if you think, because in your
we should know about that.
Thanks.
I mean, I'm actually a bit surprised to hear you being so concise to the suggestion, because I thought that the theory. At one point, I was actually wondering if we wanted something like that, as kind of deterministic prediction. I thought, of course, that's unnecessary. Like, we could read it as an A theory in which something like that happens, maybe like some growing block or a shrinking block, or whatever side you want to see from. But you can also just see it as a B theory where there are, at every time there are facts about propensities, and at later times some of the other propensities obtained. And the branches that that become irrelevant are just they're just treated in the way that someone like you certainly was a coordinator who treat branching time. So they're just things that don't concern the real world, just other possible world. So do you really want to read these as in theoretic terms, or are you just open for?
I was hoping that you could tell me what I am from. I came to the philosopher to ask it. No, I mean, really, I know a bit about these A theory, B theories of philosophy of time, but I'm really not familiar and only very superficially. So we have discussed with other philosophers. Yeah, no, I don't commit to any of these views. I was just trying to present you. I think it's consistent in itself. The view of these potentialities. How you put time on it is still, I think, a long way to go. I would be very happy if we discuss more with all of you about this, and you tell me more what are the positions out there and what they are compatible and what they fit. So as non-committal, my comments.
Good, yeah. These are the people to talk to.
Good.
Thank you. You spoke about non-Pomeranian probability theory, and that there might be one point which must be dropped. It seems to be essentially base rule. And then you draw an analogy which I found quite interesting to non-Euclidean geometry. And now there's the following question: in non-Euclidean geometry, we know about a parameter which leads back to Euclidean geometry, which is essentially the curvature. Are you aware of any parameter which could lead back from non-Pomeranian probability theory to what we are classifying?
Short way.
I think the answer is yes.
I
It's not like continuous.
Exactly.
It is going from a non-Boolean lattice to a Boolean lattice. That would go from its quantum case to the classical case.
What would be the physical parameter?
It's not a parameter. It's really Boolean or not Boolean. It's dichotomy here.
Okay.
I don't think there's a continuous
Yeah,
in
exactly.
between.
Yeah. I'm not sure that it can be done. But
In an H bar going to zero. I think that's easy efficiency.
In a way, you get the discontinuous switch from Euclidean to non-Euclidean, the moment you turn on the curvature, just anything. And that, difference, it's also in some sense physical things, I guess. Because the structure changes, like, anyway, so Enrico,
Yeah,
is it you or Maria?
well, I have a question, but first I should read Maria's questions since she was patient enough to write them down. So I can read them. So the first one is the question about what its propensities really are. So the overarching question is, what is the ontological difference relation between propensities and propensities of the system? So at one point, it seems that propensities are causal relations between events. They are also characterized as quantified tendency towards measurement outcome. So they seem here more like relations of becoming or as a part of a process towards determining properties. But later it seems that propensities get determined spontaneously. So is it propensities that get determined when there is a measurement of the properties of the system? And why not consider the propensities and measurement outcomes as different expressions of the system properties? So this is one. And then there's another question, which is that on slide 19, apparently you wrote that potentialities are not governed by necessity in determinism. Question. Aren't propensities precisely determined by the quantum state? In that case, in what sense are they not necessary? Is everything clear, or whether I ask?
Just guess to remember.
Yeah, no, I have it written down. So.
Okay. Yeah, so about the first one was propensities are all of that. But the point, well, they clearly are the potentiality. So you have to think of them as you have to think of them, where is the camera here? Here. You have to think of them as the primitive in this approach. So it's not that it seems that you are trying to get back why do you introduce propensities instead of talking about the properties. So the properties somehow emerge from the propensity when the propensity gets certain. So the properties of what we call the properties of the system in the standard way, when we think of a system, the bottle characterized by its size, exactly the width of this point, etc. These are all manifestations that you measure of certain things that the propensity was already actualized, or at least up to a certain degree that you could measure. So this likelihood became very, very close to certain or even certain. So if you want to talk at the ideal level, these propensities are what everything is to be said about the system is the propensities. It so happens that some propensities are certain. And if all these propensities are certain, then you can get back to the standard view that you have of all the properties of the system that possess properties of the classical view of a system. And the second question was
the second question that you said that the propensity is not governed by necessity, but then the propensity is precisely determined.
Okay. Yeah, that's a problem. Yeah, that's a problem. That's a problem in the sense that these propensities somehow they evolve in time. So everything that there is to be said about the system at a certain, if you pick a certain time, it's the collection of its propensities now. But these propensities can change, and the way they change, we don't know. And of course, I mean, if you think of the quantum state as the collection of the propensities, we do know how it evolves. We do know how this evolves unless you collapse it at some point. But so you can think of propensities to be spontaneously changing in time, that they get more determined, for instance. Or you can think again, as like in the quantum measurement problem, that you go there and measure, and maybe you measure with a precision of a certain amount of the millimeters, and you want to know how this table is big, and then you are somehow forcing the table to get this many, up to this precision. It has to get certain. You have to actualize these many. Well, you have to narrow down the propensity to be up to that precision actualized. So in this sense, but how in general is the dynamics that govern the propensity? It's an open problem that I don't think even there's a I don't know how. It's an open problem that I don't know how to approach.
So we are talking a lot about this measurement problem, which we believe happens also in this indeterministic view of classical mechanics. And it may give the impression that this is really a problem and the easy solution is just to go back to real numbers and Boolean mechanics. My friend there. But I think this is wrong, because in the orthodox view of classical mechanics or in Boolean mechanics, you would have the equivalence of the measurement problem is to say that all these digits, including the digits that we will never measure, have a value. And how did this value happen? Is it given by God? Is it given by us measuring them? Is it given by our wishes to believe in determinism? What is determining these initial conditions to inaccessible accuracy? And I think this is just the equivalence to the measurement problem in deterministic theories. So I don't think you avoid the measurement problem.
So Enrico, we have one question.
Not from Maria, I have a question too.
From you.
No, from me, yes. Yes. So, well, one very quick thing, because this open past thing, you kind of hinted at it, you didn't allow it, but it's kind of interesting because you were kind of discussing manifest paradox, right? So you have these two conditions, and you say we should keep this propensity as causal, but we should kind of somewhat relax the form of paradox. And the causality condition was basically a condition that the past does not depend on the present, right? And I was kind of curious how then you go forward and through these propensities, you kind of derive the fact that the past is over there. I was kind of curious, how is that compatible with the idea that the past is independent in the sense that you have the probability of the effect, the causal and the effect is zero, is actually compatible with this idea that you have an open past. And so you presumably have some sort of like trivial dependence on the present of what is behind it.
Yeah, thanks. The open past comes about it abruptly in this in the sense that it doesn't come really from the nature of propensities, but it comes more from, so I don't even know if we call them propensities, the one of the past. I don't think so. Anyways, it comes from the fact that we want to impose finite information. And so once you have like the propensities role is to explain the asymmetry that we observe between past and future. So somehow these propensities define, as I told you, the present, and then you have this graph where the recorded past is only propensities that have actualized, so it's only 0 and 1, whereas the propensities of the future can be any possible number. Therefore, the amount of information that lies in the past, it's easier to be compressed because it's only strings of zeros and ones, whereas the information about the future requires to have like a arbitrarily complex rational numbers, let's say. So really the amount of bits that requires to record the past with these propensities is low. But if you want to have an overall finite information so we take a physicalist approach to information. And if you believe that the universe is made of finitely many degrees of freedom, then there should be a maximal amount of bits encodable in the universe. Therefore, at some point, basically, you start erasing the past. That's the way you do. But it is not in a tendency way. It's really like somehow wiping out, the hard disk of the universe starts scrolling down, and the old information gets erased in this way. Causally related, so there is not causation relating the events from the present to the past in this sense. It's just somehow it's a global effect.
So the connection between the present and the past, even once the erasing starts.
Yeah.
It's not given by a propensity, like how is that? It's just that it disappears and
It just disappears, and you can only associate somehow. You can only say that it might have happened. So you can this like also in the literature of Dammet, for instance, and Lukasiewicz, they explain this idea that you can only say that is in the domain of potentiality, but it's not the same as, it's not a causal propensity.
kind of assignable.
You cannot assign a probability to it. You can just say it might have happened, and so it's in the domain of possibility, let's say, not of potentiality. That's the difference.
Thank you. I have a question.
Sure.
I agree with surprisingly many things you say, or at least surprisingly. Because I sometimes think we're, departing from very different sort of base tenets in a way of what we hold fixed. But I think that somebody who wants to defend an indeterministic interpretation of quantum mechanics is well advised to go down that road. That's a very attractive and natural way to develop that theory, the metaphysics of that. But I do have one question. There's something I don't understand. Here's one way to characterize. It's a little bit of a question to both of you, really. This is why I'm looking at both of you. So in quantum mechanics, that one way to formulate the measurement problem is to say that there is a problem, a tension between the following three propositions. The wave function completely captures the state of a system. The state of the system evolves according to a linear equation, and we have determinate measurement outcomes. That seems not possible to maintain all of these things. Something needs to go. What would be an equivalent way of sort of make salient exactly the way in which the analogous way in which the non-standard classical mechanics has a measurement problem? Is there a way of similarly characterizing it? I believe so. And so what would be the state descriptions and dynamics which are inconsistent with the fact that there are measurement outcomes?
So for the state, it is not, as Flavio said, it's the collection of these propensities. And now the evolution, let's see, it's a Newtonian equation, the standard Newton equations. And if you have that, if you apply that to a chaotic dynamical system, so you have this kind of indeterminacy, the initial condition, because of these propensities, but they would grow such as, for instance, the weather becomes completely undetermined. It's at the same time, superposition, classical superposition of raining and sunny. And then at some point it has to behave as sunny or raining. So you have this unique measurement outcome. And just the Newton equation doesn't lead to either sunny or rainy. It leads to both, because you have the two paths. So the small initial indeterminacy grows to a big indeterminacy.
I see. Yeah, that's actually very helpful. Thank you very much. Just like the Schrödinger equation is deterministic in the sense that there are uniqueness and existence results for these differential equations. There are, of course, similar results for the classical equations. If you take the states to be in the reals and way, if you truncate that information, of course, then you lose that. If you say, of course, then, and that is the complete state description.
Exactly.
There's nothing beyond that. That is the
We don't truncate the opposite. We are the correct ones, and you guys are adding it.
Except it's unexpected, but I see what you mean.
Yeah.
So,
So if I made the initial, what is the quantum state, which is the sign in the normal story that you feed to the Schrödinger equation to evolve, now is a finite region of space-time, and this is mapped deterministically to another block of space-time, of space. So the two states at the beginning and end, they are deterministically mapped in the same way that Schrödinger does. But then you want also to have the single outcome when you measure. You don't want to have the whole
And the
phase
general-
space. You want to collapse it to relocalize it somewhere in phase space in this sense.
That's good.
Yeah.
That's very good. There's, well, we're out of time, I'm afraid. I have more questions, but maybe over dinner. So please join me in thanking Flavio again.